Thank you very much, and thanks to the organizers for giving me the opportunity to speak here. So my talk follows a bit in the spirit of Shota's, but I will study a slightly different context, the case of ADS3 CFT2, of course. Here, I guess we all love CFT2, but I will study it by integrability, and I will show how the integrability techniques, similar to the ones that Shota introduced, can be applied here to learn something new about the dual CFT2s of certain ADS3 spaces and about ADS CFT in general. And for this talk, I will be working mostly with two ADS3 backgrounds, ADS3 cross S3 cross T4, or ADS3 cross S3 cross S3 cross S1, so two spheres. And I won't have time to say much about them, but one thing to know is that these are among the most supersymmetric backgrounds that you can consider. They have 16 supersymmetries. In the first case, they are collected into two copies of PSU1,1/2. And in the second case, into two copies of the D21 alpha exceptional superalgebra. And sometimes these backgrounds go under the name of spaces with small, so-called, or large n equals 4,4 superconformal symmetry. And the difference between small and large is due to the fact that one has an additional R symmetry of SU2, which comes from the presence of the second sphere. And of course, this is a way of writing it that makes you immediately think about the dual conformal field theory in two dimensions. For the first space, there is a very nice and very well-studied conformal field theory that one has in the modular space of that background, and it is a symmetric product orbifold CFT, a symmetric product orbifold of T4. Surprisingly, in the second case, there is a lot of confusion about what the dual CFT is, and this is something that I will address in my talk. So these theories have a large modular space, and from the point of view of string backgrounds, you can support them with fluxes that can be a combination of Ramon-Ramon three-form fluxes or NSNS. And what I want to do is to study these backgrounds for a generic value of the fluxes and to find a very simple property of the backgrounds, which is the protected spectrum. In principle, I will give you formulas to derive the whole spectrum, but I will focus on the protected spectrum mostly. And for the first part of my talk, I will be looking at this T4 background because it's a bit simpler. And I will focusing on the Ramon-Ramon case because it's a bit similar to ADS5 cross S5, where integrability worked very well already. And the spirit is very much the one of, used in ADS5 cross S5, and I refer you to a very nice review by Gleb Aritunov and Sergei Frolov about this, how to do integrability for ADS5 cross S5. And it goes back indeed to Zamolodchikov and Zamolodchikov. Sorry? Which one? Okay, I will avoid it in future. Thank you. What is the strategy? The strategy is to look at the string nonlinear sigma model. And fixed light cone gauge. And now you have a two-dimensional quantum field theory. And then you will study the symmetries of this theory in light cone gauge. And through these symmetries, you will find a two-particle S matrix, S of P1, P2, P1 and P2 are the momenta. And you will hope that this two-particle S matrix is integrable, meaning that it satisfies the Yang-Baxter equation. And if you are lucky and you can do all these, which is possible for these backgrounds, for general values of the fluxes, then what you can do on top is that you can write Bethe-Ansatz equation, which correspond to putting your theory in a finite volume. And out of this, you find the spectrum. And this is the famous Bethe-Ansatz, TBA, quantum spectral curve, and so on and so forth. But here I want to do something much simpler. I don't want to find for you the whole spectrum because the blackboard would not be enough. I will find only the protected part of the spectrum, which is of course a bit easy, and you might wonder why go to the trouble of integrability to do something which I can find in many other ways, but there are some lessons to be learned there. So bear with me and I will comment on what we have learned at the end. Any questions so far on the strategy? So if not, I will start telling you what happens when you study the ADS3 cross S3 cross T4 background in light cone gauge. And the way to do this is that you pick a coordinate on ADS3. Let's call it T, and this is the time in ADS3. And you pick a coordinate on S3. Let's call it phi, as some great circle. And you look for the most supersymmetric string solution that you can find. And that's a 1/2 bps point-like string solution that you have. And this has charges D, energy, which is the Cartan of SL2, equals J, equals some number, let's call it ½ for the left algebra of PSU1, 1/2, and it has the same thing in the right algebra, D tilde and J tilde. And I will always use the tildes for the right part of the algebra. And this is ½ BPS because the BPS bound for this algebra, for PSU1, 1/2, is D greater or equal than J. So we are in business, and we are interested in the Hamiltonian on the worksheet, it's the total energy, and like everything in this theory, it splits in the left and the right part. So part of it is D minus J, and then there is another contribution, which is D tilde minus J tilde. So it's positive definite as it should be. And I will call this part H, and this H tilde, just to have a nice shorthand. And then I want to see which are the symmetries of this Hamiltonian, which will be the symmetries of the S matrix. And I told you that supersymmetry are halved. So in the left algebra, instead of 8 supercharges, I should have 4. And I do have 4, and they are called QA, where A is 1 or 2, or Q dagger, 1 or 2. And their anti-commutation relation are the simplest thing that you can imagine. They give you the Hamiltonian. And that's for the left part of the algebra. And for the right part of the algebra is exactly the same. So it's a very simple algebra, it's exactly what you can expect. But there is a bit of a surprise in a moment. Before the surprise, let me just rewrite this anti-commutation relation in terms of the total energy E. So I can call this E plus something, and this E minus the same thing, let's call it M, semi-sum and semi-difference. That's just a useful shorthand. So now the surprise is that you might dream of considering the anti-commutator of a left and the right supercharge and wonder what that is. And the answer is that it's not 0. It's not 0 because this algebra gets centrally extended. It's a bit strange because you didn't have such an anti-commutator when you began. But it's a feature of light cone gauge, which is very well known in ADS5, and it's a key ingredient of integrability. And it's even well known in ADS3 because Gava and Narayan already in 2002 found such a central extension by studying the PP wave limit of this story. And semi-classically, you can compute this central extension, and you find that is a simple expression in terms of the worksheet momentum P. It's not so simple because it's nonlinear, but it's not the ugliest function that you can imagine. And most importantly, it has the property that when the momentum is 0, mod 2 pi, so when you are considering a physical state, this gives you 0. So you are back with the algebra that you started. And H is some parameter which is morally the tension. So this is the algebra, and it's almost all I need to find the spectrum. The only thing that I need on top of the algebra are the representations. And the simplest representations and the most interesting are just the one on the 8 plus 8 modes of the light cone gauge fixed string. So I have 8 bosons and 8 fermions. And they are labeled by E, M, and C. And here I have, of course, another relation for the daggers, which is exactly the same thing, just because this algebra is unitary. And it turns out that it's easiest to look at the value of M. So I have M equals +1. I can check this semi-classically. And I have 2 bosons and 2 fermions that have M equals +1. Then I have m equals -1, that's another possibility, and I have 2 bosons and 2 fermions that have m equals -1. And then the remaining 4 bosons and 4 fermions have m equals 0, and I write them as 2 copies of things that have m equals 2/2 because they form 2 2/2 representations of this algebra. And morally, these guys come from ADS3 cross S3. The bosons are the transverse coordinates in ADS3 cross S3, and these guys come from T4. And another very important thing is that this representation here has a nice property. It is short. So it means that it satisfies a relation between the central charges that cannot be whatever you want, but E is related to M and to CC dagger in a simple way. And what is nice of this shortening condition here is that I can write it on a one-particle representation as a function of the momentum, and I find the worksheet energy E as a function of P. And for people that have worked on AdS5 integrability, this looks like very much like the same dispersion relation, only now M, instead of being fixed to 1, can be the modulus of M, can be either 1 or 0. And with this information, we can go and we can compute, I claim, the spectrum of the theory. And the way to do this is a bit different from usual, because normally we would have to find the S matrix, which let me say that we have done, so believe me, you can do that. And then on top of that, you would diagonalize the S matrix and write your beta equations, and we have also done that. And then what you would do is that you would try to solve them, the beta equations, and find some solutions that you write as function of the momenta. And this is something that you can do, and you would find a lot of states, protected or non-protected. But if you want to find protected states, there is a better way to do it, because the protected states are the ones that have D equals to J, which means that E is equal to 0. So I can just solve the condition that E is 0 and check whether there are states that solve the beta equation and that condition. That condition is very restrictive, as you see in a moment. Because in an integrable theory, the energies are just additive, and the energy of a state with many excitations is just the sum of the individual energies. And for this to be 0, you see that M has to be 0, and P has to be 0. So all these things will be 0. And this can happen only if I use these M equal to 0 particles that are the 4 bosons and the 4 fermions. Question? Can I answer at the end of the talk? They might come if I have time. So here they are just coordinates on the T4, and they're supersymmetric partners for the moment. And the bosons, let's give it a name, TAA dot. This is the SU2 cross SU2 on the torus, let's say. And then there are fermions Chi-A and Chi tilde A. And these guys at 0 momentum, they give you a solution of the beta equation, but the solution corresponds to symmetries. And they are the U1 to the 4th shift isometry of T4. So they are not really what we are looking for. The fermions, on the other hand, do give you new states, and you can construct states by adding some massless fermions at 0 momentum on top of your vacuum. So let me call the vacuum that I started from omega n, that had charge and half is still up there. And then I can add, for instance, one fermion chi, which I write to the left because it's charged under SU2 left. And there are 2 such fermions, chi1 and chi2. Or I can write a chi tilde. Or I could write 2 chi's, that's even more to the left. Or 1 chi and 1 chi tilde. Or 2 chi tildes. But of course, these are fermions at zero momentum, so I should not forget that their wave function is completely antisymmetric. So for these guys, there's no problem because they're different, but this will only be non-zero. This wave function will only be non-vanishing if I contrast this with an epsilon. And now it's very easy to see how to proceed. I can just keep putting as many fermions as I can. So for instance, here, 2 left with an epsilon and 1 right. Here, 2 right with an epsilon and 1 left. And here, 4 fermions, 2 left, 2 right, with 2 epsilons. And then if you look at how many states you have for each of these blocks, you see that you have 1 state here. You have 2 states here because A can take 2 values. Also here there is an A. Here you have only 1. Here you have 4. Here you have 1. And then the whole story is completely symmetric. So you get 2, 1, 2. And somebody in the audience might recognize immediately the Hodge diamond of the torus, because these fermions on the torus exactly gave you the cohomologies of T4. And this is comforting because this is exactly what you need to have the protected spectrum of the symmetric product orbifold CFT of T4. These are exactly the thing that count the BPS states of the symmetric product orbifold CFT. So with very little effort, we have rediscovered that the dual of this thing should be a symmetric product orbifold of CFT of T4, or at least should have the same protected spectrum. And this was known in the literature. Let me do something which is a bit new because this was known. And one thing that I can do with almost zero effort is to consider mixed flux, an SNS and Ramon-Ramon. That's typically very difficult. And here, let's try with the green. It's very simple because all that change, the algebra is the same. All that change are the representation. They get a bit deformed. And they get a bit deformed because the mass gets a shift, which is proportional to the momentum by a constant kappa here. And this constant kappa is proportional to the amount of an SNS flux. And my formula here gets also modified by a similar shift. But you see that all the words that I said go through in the same way, because for this to be 0, it's still true that M should be 0 and P should be 0. So the protected spectrum does not change if I add some SNS flux. So that's nice. Now let me do S3, S1. And that's also relatively easy. And I can start from where I was before, but now I cannot really reuse all of the blackboard. I can reuse most of the blackboard. Let's see. So the idea is that now we have 2 spheres, and this will change a little bit the story, because here I have to pick a phi prime and a phi double prime. And the resulting string solution will be 1/4 BPS. And it will be labeled by the energy and by 2 cartons, which 2 SU2 labels, which are indeed 2-1 alpha. And this particular solution, which is the most supersymmetric that you can get, will have D equals J prime, which is one of the 2 SU2s, equals J second for the left, equals n half, and the same thing in the right. And the BPS bound is now D greater or equal than alpha J prime plus 1 minus alpha J double prime. Now this alpha is the parameter of the 2-1 alpha, and just to remind you, I will write it here. Alpha is related to the ratio of the radii of the 2 spheres. So it's some geometric property of your background. So note that you could have gotten a BPS state by doing something very much more general, by picking one guy in some way and J2 different, playing around with alpha, but we have a very simple BPS state. And everything goes through almost exactly the same way. Only that since the algebra is 1/4 BPS, I have to erase all these labels, and I have alpha of the supercharges. I don't have a 1 and a 2 anymore. But the algebra is the same, the central extension is the same. The shortening condition is the same, and the only thing that changes is that now the masses here are slightly different, and I will write them here in some nice colors, so you can all ponder on this. Let's see if orange works. So now, M can be alpha, 1 minus alpha, 1, or 0. And there are 2 bosons and 2 fermions per label here. But just like before, the only thing that matters is the case in which it is 0, because otherwise I don't get the BPS spectrum. So what I have then is that I can construct the BPS states in the same way as before, and I will do it here on the side. So I have my vacuum, omega n, which is the one now with those labels there. I can put 1 fermion in the left, or I can put 1 fermion in the right. Or I can put both. And that's it. It's a much smaller diamond. And note that all the states have j prime equals to j double prime in the left, and j tilde prime equals to j tilde double prime. Because we started from such a state, and adding just one of these fermions does not do anything. And this is very interesting because in the literature, since the 90s, there was a supergravity argument that told you that you could have BPS spectra for any values of j prime and j double prime. And then people have tried very, very hard to find the dual CFT to this thing. And they failed because they said, oh, there are some CFTs that almost work, but I have a BPS spectrum which is much, much smaller. So there is a nice paper by Gukov, Martinek, Strominger, and Moore. Now you can go with this knowledge and revisit those proposals. And you can even check that the supergravity argument, this has been done by Gaberdiel and collaborators. You can check that the supergravity argument was a bit too quick, fast, and loose. So you can derive the correct supergravity spectrum, which is this one. And you can recheck the proposal for the dual CFT, and you can find that there is at least a class of good CFT duals that seem to work. And they work when alpha is written in terms of some levels as 1 over an integer. So these are not really all the 1 over k, where k is equal to 1, 2, etc. So these are not all the values of alpha that you can hope for, but still it's better than nothing. And a hint to guess what is this CFT, either you know the papers, or you go look at the latest paper, the paper by Gukov, or you go look at the latest paper by Matthias. Or the hint is that this is also a Hodge diamond. And if you fill in the gaps, you will find out the Hodge diamond of what. And from that, you will find that it's a symmetric protoorbifold CFT of that particular space. I didn't bring a prize for the people that guess right, so I'm sorry. Now, the last comment that I want to make in the, how many minutes? A couple of minutes, I guess, yeah. Is what else we can do with this. So we learned something nice and new about the CFT dual of S3S1 with very little effort. But there are more general questions that we can ask. And one thing that is interesting to ask is, for instance, what are exactly these symmetric protoorbifold CFTs? There are some nice free theories. They are morally the equivalent of n equal 4 superambiguous at a free point. And they should sit somewhere in our integrable moduli space. So where do they sit? Can we say something about that? And I will just tease a little bit what maybe we can say. This is work in progress, so take it with a pinch of salt. And I will tease it for the case of T4. So the idea is that for T4, you have a Hodge diamond which looks exactly the same, only that those are vacua of a twisted sector of twist 10. And the sides there, sorry, the chi's should be replaced by fermions that have E equals J. And you have exactly the same number of such fermions in the symmetric protoorbifold of T4. So then you can say, what happens if I construct excited states? And these excited states have a fractional mode number because you're there in the twisted sector. So how do I choose the parameter of my theory? And the first thing that I should point out is that if you're in the symmetric protoorbifold of T4, and you're not deforming it in any way, this commutation relation should really be 0. There is no way that this can be non-zero. So I should take H equals 0 in the symmetric protoorbifold of T4, and my energy becomes much simpler. It becomes linear. And then I can try to find a state in a spin chain that has that energy And it's very tempting to say that this is just some T of P state on some integrable system of size n, which gets quantized with condition e to the Pn equals 1. So P is 2 pi k over n, where this k is meant to be exactly this k here. So this is interesting, and you can make it a bit more precise. These are ideas that have been in the, they have been discussed a long time ago by Gava and Narayan in 2002, by Rastelli and others, I don't remember how many years ago. But now we have this integrability machine, and you can try to make it more precise. And for one thing, you can check that all the representation, the 2/2 representation that I sketched, you can make them fit exactly in representation of the excitation of the symmetry product orbifold CFT over suitable vector. Of course, then you want to ask more. For instance, can I reproduce the whole partition function of the symmetry product orbifold at the free point? Or can I deform it a little bit and see the interaction, see that I turn on some string tension? And this is very much work in progress, and I think this maybe is a place to stop. Thank you.